Hello and welcome to this NHP webinar on the utilisation categories for electromechanical contactors. My name is Ron Ryor and I'm a product specialist and technical training leader for NHP electrical engineering products. In this presentation, we will look at utilisation categories for electromechanical contactors and motor starters from AS NZS 60947.4.1. The goal of this presentation is to cover the following points for an understanding of the different load types which are switched by contactors, the utilisation categories assigned to these load types, the testing performance requirements for the different categories, and how utilisation categories may need to be interpreted in some applications, where technology of some electrical equipment types have changed in recent times to improve energy efficiency. Whilst contactors are predominantly utilised for switching of motors, they can be utilised for the switching of many different electrical loads. Today we are looking at AC switching only for the following load types: resistive, motors, inductive and capacitive, and lighting applications. The testing currents for making and breaking capacities of each utilisation category are listed in Table 7 and Table 10 for conventional operation performance. The testing emulates the different current profiles for the different load types during making and breaking operations. For each test for making or breaking is done at 5% above the UE nominated operating voltage, with the power factor varying depending on the category and IE rating. The contactors are subjected to a defined number of operating cycles, having rapid cycling with an on time of 50 milliseconds and then off, depending on IE, from 10 seconds and up to 4 minutes for the largest contactors. The load types for utilisation rating of AC1 are of a resistive load type or slightly inductive in nature. As the contactor closes and applies full voltage, these loads have a starting or inrush current which is equal to its full load running current, with running current seen as the contactor opens. Resistive heating elements are, for example, used in water heaters, industrial ovens, and air conditioning plants. The AC1 rating can also be used in power distribution for load shedding applications, as normal switching is of mixed load types with the power factor in the order of 0.8. The testing for AC1 duty is performed at a power factor of 0.8, with conditional performance at its rated current and verified to make and break at a 50% higher value. The nominated AC1 is one of the common ratings which is designated on the rating nameplate of a contactor. In this instance, it shows a rating of 32 amps for voltages up to 690 volts. This is based on a 40-degree ambient temperature. However, for some contactors may have a D rating factor for higher specified ambient temperatures, with 60 or 70 degrees C being listed in technical data. The AC3 utilisation is the most common for a contactor, as the majority of applications are for three-phase squirrel cage induction motors. The starting of a motor by closing a contactor to apply full voltage to the motor terminals is referred to as direct online or DOL starting. This AC3 utilisation category makes allowance for the loading of the contactor by increased making currents when a stationary motor is switched on. Typically, a motor has been designated as having an inrush current 6 times its full load running current when voltage is applied and motor speed is 0. Whilst at stopping, the contactor only has to break a current equal to the motor's full load current rating. The test conditions for AC3 duty, making and breaking capacity, is at 8 times its rated current, with a power factor dependent on the IE rating, with additional making test at 10 times IE and the conditional making and breaking at 2 times IE. The nominated AC3 is the most common rating which is designated on a contactor's rating nameplate. It shows a rating in kilowatts for motors at different line voltage values. The contactor can have AC3 ratings at different operational voltages, and whilst in some instances the AC3 rating may be the same, the AC3 amp rating will reduce at higher operating voltages. Electrical endurance curves are provided to guide a contactor's expected operating life for motor applications based on gradual electrical wear of the contacts, which occurs during making and breaking of the load, where arcing occurs and contact material vaporizes. The verification of these is done through testing as set out in Appendix B, Part 3 of 60947.4.1. For AC3, the contactor closes with 6 times rated current and opens at rated current but at 17% voltage, which equates to the voltage across the contactor as back EMF is still present from the rotating motor. The number of operations completed is in the hundreds of thousands or millions depending on the manufacturer's specification and provides real-life performance data for the contactor. The testing performance criteria for contactors has been specified for over 50 years. When the testing standards were first written, a typical motor had a locked rotor value of 6 to 7 times full load current. As motor efficiency has improved, today with IE3 Premium Efficiency motors, they are considered to have a locked rotor value of 8 times full load current. However, it is not uncommon to see 9 times. Selection of a contactor based on its standard AC3 kilowatt rating can be used, but it would have a much reduced electrical life. To maintain the electrical endurance value of a contactor, derating of 20 to 25% for a premium efficiency motor switching can be applied. For example, a 7.5 kilowatt 16 amp AC3 contactor with a 25% derating is 12 amp AC3, so would be suited for a 5.5 kilowatt IE3 Premium Efficiency motor. However, where the locked rotor current is known for a specific motor, to calculate the contactor's reduced rating, which allows for switching the IE of an IE3 motor, this formula may be used, where a contactor's IE for an IE3 motor is the contactor's standard AC3 reduced by how much the locked rotor current of the IE3 motor is above the tested 600%. The AC4 utilisation is the most severe for contactors when switching motors. Inching or jogging is used to rotate a motor into a position for the mechanical purposes of a connected load. In this application, the motor is energised by closing the contactor, but then opening the contactor whilst the motor is drawing close to its locked rotor current value. Plugging is a method of bringing a stopped motor but is still rotating with a high inertial load like flywheels and fans to a stationary position quicker. Once the motor contactor is opened, the plugging contactor is energized with reversed phase rotation, which attempts to reverse the direction of the motor until the motor is close to zero speed. This application causes severe electrical stress on equipment and mechanical stress on the connected load. The test conditions for AC4 duty, making and breaking capacity, is at 10 times its rated current, with additional tests made at 12 times IE, with the conditional making and breaking at 6 times IE. Testing for electrical endurance curves for AC4 utilization is verified by closing with 6 times rated current and opening at 6 times rated current. There is reduced requirements for inching and plugging duties for contactors, with alternatives of VSDs used for positioning and braking applications, or DC injection brake units being used for these applications. This utilization category is for slip ring wound rotor induction motors. These motors normally start with resistances in the rotor circuit, which reduces the inrush to the stator and the making currents required by the contactor. The typical value is 2.5 times. The wound rotor motor was principally used for speed control or high starting torque requirements. However, with the advent of utilizing a variable speed drive to control a standard induction motor for these applications, there are now limited applications for this utilization category. The test conditions for AC2 duty, making and breaking capacity, is 4 times its rated current, with the conditional making and breaking at 2 times IE. This utilization category is for Hermetic refrigerant compressor motors, in which the compressor and motor are integrated and housed within the pressurized gas envelope. The inrush and locked rotor currents are less than standard squirrel cage motors, so these utilization ratings have a lower making and breaking capacity. AC8A is where the motor control has manual resetting of overload releases, and AC8B with automatic resetting of overload releases. These ratings are utilized in HVAC refrigeration applications, which do not utilize inverter drives. The AC7 ratings are not defined in 60947.4.1, but are from IEC 61095, which for electromechanical contactors for household and similar purposes, where the rated conditional short circuit current is less than or equal to 6 kA, and the operational voltage does not exceed 440 volts AC. AC7A ratings are for slightly inductive loads, similar to AC1. AC7B ratings are for motors, similar to AC3. The AC7C ratings are for power factor corrected discharge lamps, with power factor like 5A, but also similar to AC6B for capacitor switching. It should be noted that these ratings are for household applications and the electrical endurance is less than industrial contactors. When a low voltage transformer is switched on, there is a short-term inrush current surge from energization of the magnetic field. The peak surge inrush currents vary with the transformer construction and voltage phase angle, but can be up to 30 times the transformer rated current. The factor N of a transformer is defined as the inrush peak versus the operational current. Whilst the N factor is specified by the transformer manufacturer, if it is unknown as a guide, the following factors are given. Small transformers up to 1 kVA use N factor of 20, and above this use N factor of 30. The contactor needs a high making capacity to avoid contact welding upon closing. With standard 60947.4.1, providing that AC6A rating can be calculated from the tested AC3 switching capacity. For an N of 30, the rating equals 45% of the AC3 IE. For other N factor values, these are generally listed in the contactor's technical data. Switching of capacitors can be the most severe duty for a contactor, with extremely high inrush peaks possible where closing occurs at the voltage peak of the sine wave. AC6B is the utilisation category for the switching of capacitor banks in power factor correction systems. The testing conditions for AC6B duty making and breaking capacity is at 1.5 times its rated current, with the conditional making and breaking at rated IE. However, the testing is performed with actual banks of capacitors of a value to the testing current, which provides the high initial inrush of the application at a low power factor. In power factor correction systems, a standard contactor would need to be greatly derated from its AC3 value to cope with the very high inrush currents. So inductors are included as part of the design, and contactor versions for capacitor switching, which are designed to include early make auxiliary, which insert resistances into the circuit to pre-charge the capacitors before the main poles are closed to reduce the inrush peak seen. Whilst you would think incandescent lights being a resistive load would have a lesser impact on contactor switching, as the filament is made from tungsten, which has a very low resistance when cold, hence there is a high inrush current at turn on, up to 15 times running current. The testing for AC5B duty is with conditional performance at its rated current and verified to make and break at 50% higher value. However, the testing is performed with actual incandescent lamps, which provide the high initial inrush of the application. Halogen lamps are similar in behaviour, even when supplied via a transformer or electronic ballast. They have similar inrush currents as incandescent lamps. As incandescent lights are highly inefficient, they have been phased out in favour of halogen compact fluorescent or LEDs. Fluorescent lighting and discharge lamps like mercury vapour, metal halide or sodium vapour are covered by Utilisation Category 5A for contactor selection. These lamps have transformer ballast starting circuit which causes an inrush current of 2 to 6 times, and may have current limitation circuitry which maintains a higher start current for up to 10 minutes, whilst the lamps get to full illumination. The testing for AC5A duty is verified to make and break at 3 times IE with conditional performance at twice its rated current, with the power factor of 0.45. These testing conditions are for non-power factor corrected lights. As it is normal for light fittings to include power factor correction, manufacturers' selection tables for contactors may also include limits of total capacitance and fault levels. Discharge lamps with inductive ballasts have a low power factor, so correction capacitors are connected in parallel with the line voltage. So upon closing the contactor, it sees the inrush current of the capacitor. Whilst it has been generally accepted that the inrush was 20 times rated current, as correction capacitor sizing has increased to provide power factor greater than 0.9, inrush levels are now much higher. The worst case scenario occurs if power application corresponds with the peak of the AC supply waveform and can be dependent on the prospective fault level at the installation. We have seen in testing a 2000 watt metal halide lamp with 80 microfarads of correction with inrush currents of 35 times, and a 600 watt sodium vapor lamp with 60 microfarads correction have a 200 microsecond peak inrush of 100 times. As AC5A is not suited, and whilst selection may be based on AC6B capacitor switching, it can be easier to select based on the known making capabilities of AC3 ratings. As AC3 testing has making tests completed to 10 times rated current and to allow for 35 times inrush, the AC3 rating of a contactor should be in the order of 3.5 times the lamp's running current. LED lighting uses lamp drivers and control boxes to power the LED lamps. These drivers and control boxes are electronic based, so startup and operational current loads should be obtained from the lighting manufacturer. Examples seen of drivers with 66 times for 300 microseconds or inrush of 80 times for 400 microseconds, and control boxes with 12 times for 2 milliseconds have been seen, so ratings vary widely. As the inrush data varies widely, depending on the type and manufacturer, the selection guide as used for floodlighting could be used with AC3 ratings of a contactor in the order of 3.5 times the lamp's running current. This concludes the webinar. Thank you for joining us for this webinar. I trust you found it beneficial and helped in your understanding of utilization categories for electromechanical contactors.